Okay, so moving on to 7.5. 7.5 is all about integrating rational functions by partial fractions. And so I wanted to start with a brief review of partial fraction decomposition for those of you who are maybe unfamiliar with the technique. And then we'll look at, I think I have 5 examples prepared. So by the way, I'll post these notes so you can print them off. I'll post these with the lecture so you can print them off and kind of follow along. But I modified these from a pre-calculus class. Anyway, the idea is that, of course, we can always add to rational expressions, find common denominators, right? Add the numerators. But for the purposes of integration, we actually prefer the left-hand side. Okay, it's nicer to work with. In fact, these are just like natural log type of situations, right? Whereas the right-hand side is a little bit more difficult. So what we really want to be able to do in calculus is go backwards, go from here and end up there. So we want a method for finding a and b such that this expression is equal to a over x plus 3 plus b over x minus 1. So what we do is we begin by assuming that such an expression exists, okay? And then we solve for a and b. We do that by, first of all, multiplying through by the denominator to clear the fractions. And then you can do one of two things, right? You can either regroup the terms so that you collect all of your terms for x and all of your constant terms, and then you can do what's called equating coefficients. And what that means is that if 5x plus 7 equals a plus b times x plus negative a plus 3b, then it must be the case that a plus b equals 5 and that negative a plus 3b equals 7. And so then you get this system of equations that you can solve, right? The other strategy is, so that's called equating coefficients, right? The other strategy is that you can just plug in different values for x to get certain terms to cancel off. I don't know what this is called, so I'll call it the cancellation method. But the idea is, you're starting with this expression, you clear the fractions, and then you can just choose nice values for x. So for example, if you let x be 1, then the a term will go away, right? And over here you'll get 5 times 1 is 5, so you get 5 plus 7 equals a times 0 plus b times 4, or in other words 12 equals 4b, so b equals 3. And if you let x be negative 3, a similar thing happens with b, right? It disappears, and then you're able to solve for a. So this is a really nice method that sometimes works quicker than solving the system that you would get by equating coefficients. Sometimes it doesn't work out though, right? Sometimes the solving the system of equations is inevitable, right? But you're welcome to use either method. Just for the purposes of knowing what I'm talking about, let me so that you understand what I'm talking about, let me define that these little fractions in this previous example, right? These are called partial fractions. And when you add them together, that's called the partial fraction decomposition of the original expression. So we want to find the partial fraction decomposition of these kinds of things so that we can integrate them. Now, one thing that we need to sort out still is that here we assumed that the format of the decomposition would be this. Well, how do we know that, right? Well, I'm not going to take you through any proofs or anything, but here's what we can say, right? So here's the kind of general rule of thumb. So note that if a polynomial is completely factored over the real numbers, then its factors are all either linear factors or quadratic factors. So now here's how you deal with this. If you have linear factors, okay, so let's say that a lowercase q equals x minus a is a linear factor, right? And let's say that it's repeated m times. M could be 1 or 2 or 3, right? But it's repeated m times in the complete factorization of capital Q, okay? If that's the case, then the portion of the partial fraction decomposition of p of x over q of x that corresponds to lowercase q is a1 over x minus a plus a2 over x minus a squared, and so forth. You kind of build up the exponents one by one. So a3 over x minus a cubed, a4 over x minus a to the fourth, until you get up to m, where m is the number of times that linear factor is repeated. So if it's not repeated, well, then you would just stop here, right, with the first one. If, on the other hand, your factor is a quadratic one, then you do a similar thing, but the numerator has to be ax plus b instead of just a. You have to have ax plus b in the numerator. So I'm assuming that this is probably old news for most of you, so I'm kind of running through it pretty quickly. If it's not old news for most of you, I think it'll become clear as we look at some examples. So let's look at this set of examples. And here, I just want to give the form of the partial fraction decomposition. I'm not actually interested in solving for what the partial fraction decomposition is. I just want to make sure that you can get out of the starting gates. So let's say that you have this expression, 3x plus 26 over x squared plus x minus 12. To find the partial decomposition, the first step is always to factor the denominator completely, right, over the reals. So, so the denominator, excuse me, so the denominator here would be, if we factor that, that would be x plus 4 times x minus 3. The numerator, of course, is still 3x plus 26. And now notice that these two factors are both linear factors, and neither of them is repeated. So the partial fraction decomposition here would look like a over x plus 4 plus b over x minus 3. Okay? And then you could solve for a and b from there. But that's where I'm going to stop. Okay? Let's look at the next one, right? So for the next one, we've got, well, first of all, I can factor out an x. Oh, and then that's a perfect square trinomial, right? So this is going to be x times x plus 1, or x minus, sorry, minus 1. That should be an x minus 1 squared. Right? Okay. So now you've got two linear factors, but this one is repeated twice. So the partial fraction decomposition would look like this. You'd have a piece for the x. You'd have another piece for the x minus 1 to the first power. And then you'd have a third piece for the x minus 1 to the second power. Okay? And then again, here you'd have to solve for a, b, and c to figure out what the partial fraction decomposition here is. Okay? Here's another one. So we'll begin by factoring this. We can take out an x, and then we'll be left with x squared plus 2. Now, we could factor this further if we were allowed to factor over the complex numbers, right? You would factor this as x plus I root 2 times x minus I root 2. But we're not working with the complex numbers in this class, so this is completely factored over the reals. So you have a linear factor and a quadratic factor. So the partial fraction that corresponds to the x is just going to be a over x. But the partial fraction that corresponds to the x squared plus 2 is going to be bx plus c over x squared plus 2, right? Because it's a quadratic. Right? So notice the difference between this one and this one. Here we have a quadratic factor repeated once. Here we have a linear factor repeated twice. Okay? And if you're thinking, well, isn't this a quadratic factor? Yes, but this isn't completely factored, right? So the idea is step 1, completely factor it, which in this case would look like this. And then step 2, break it down. So last one. This one's already factored for us, thank goodness. So it looks like I've got a linear factor, and then I've got a quadratic factor that's been repeated twice. So what does the partial fraction decomposition look like? It's going to look like, well, you're going to have, this is a linear factor, so it's just going to be a over x minus 1. And then this is an irreducible quadratic factor, right? You can't factor that any further. So it's going to look like bx plus c over x squared plus 4. And then because it's repeated twice, you have to have a second copy. Dx plus e over x squared plus 4 squared. Okay? And then the idea is that, of course, you're going to solve for a, b, c, d, and e in the next step, right? But this is the idea behind partial fraction decompositions. And then once you've got the format down, well, then you solve for the coefficients by either using the cancellation method, or by using the equating coefficients method, or by some combination of the two. One last thing to point out, and then we'll look at some, and then we'll do some integration. So in the examples above, the degree of the numerator was always less than that of the denominator. Like here, the degree of the numerator was, or sorry, let me show you what I'm pointing at. Here, the degree of the numerator was 1, and here the degree of the denominator is 2, right? Degree of the numerator is 1, denominator is 3. Degree of numerator is 2, denominator is 3. Here, the degree of the denominator is 4, or numerator, sorry, is 4, and the degree of the denominator would be 4 plus 1, so 5, right? Degree 5. Anyway, but this begs the question, what if the degree of your denominator is greater than the degree of your numerator, greater than or equal to? Well, if that's the case, then you can just use long division, right? Just do long division to rewrite p of x over q of x as some other polynomial plus a remainder, okay? When you do that, the degree of the remainder will always be less than the degree of the denominator, okay? And so there's no need to consider any cases where you have quote-unquote improper rational expressions where the degree of the numerator is greater than or equal to the degree of the denominator. Because if you have that situation, you can just do the long division, and then the piece that's left over for you to break down by partial fraction decomposition, you can just use, this method here. So let's do it. Let's evaluate some integrals using this idea. Okay, so with this one, I mean, potentially you could like complete the square and then do a trig substitution or something, and that might help you here. But here's another way that you could do it using partial fractions. You could say, well, this is the integral of dx over x plus 2 times x minus 1. And now I'm just going to do some scratch work, right? I'm going to say, well, this fraction is, so 1 over x plus 2 times x minus 1. I know that its partial fraction decomposition should look like a over x plus 2 plus b over x minus 1. And then if I want to solve for a and b, I can multiply through by the x plus 2 times x minus 1. And that would give me 1 equals a times x minus 1 plus b times x plus 2. Sorry. Okay. So you could equate coefficients, or you could do this little trick. You could say, so let x be 1, and then we get 1 equals a times 0 plus b times 3, right? Okay, so b is 1/3. Okay, and then we can say let x be -2. And then you're going to get 1 equals -2 minus 1 is -3. So you're going to get a times -3 plus b times 0. That means a is -1/3. Okay, so then what we end up with is this, right? So this integral is really the same thing as, I'm going to put b first. I mean, it doesn't matter, whatever. So I'm just going to pull out the coefficient though. So I'm going to call it -1/3 times dx over x plus 2 plus +1/3 times dx over x minus 1. Okay? because 1 over x plus 2 times x minus 1 is equal to negative 1/3 over x plus 2 plus 1/3 over x minus 1. And so I've just split the integral, but the rest is history, right? This is just ln of x plus 2 plus, negative 1/3 plus positive 1/3 times the natural log of x minus 1 plus c. Okay, and that's all she wrote on that one. So, so not terrible. Okay, just making sure I was recording. Okay, next one. So we've got 2x plus 4 over x cubed minus 2x squared. So I'm going to start off by finding the partial fraction decomposition. So this is going to be, I'm going to have 2x plus 4 over, well, I know I can factor out an x squared, and then I would be left with an x minus 2. Okay, now don't be fooled. These are all linear factors. This is a linear factor of x that's been repeated twice. And this is a linear factor of x minus 2. So the partial fraction decomposition should look like this. A over x plus b over x squared plus c over x minus 2. And then I can clear the fraction by multiplying through by that denominator. I end up with 2x plus 4 equals a times x minus 2 plus b times x minus 2 plus c times x squared. Okay. So I think if I do my little cancellation method, I can solve for c if I let x be 2. And if I let x be 0, I can solve for b. Solving for a is going to be a little bit trickier, though. But, you know, I might as well use cancellation when I can, I suppose. So I'm going to say, ooh, I'm going to run out of space probably. So let me do some scratch work. I'm going to say, if I let x be 2, then I get 2 times 2 is 4 plus 4 is 8. So I get 8 equals, that's going to be gone, that's going to be gone, and that is going to be 2 squared is 4, so I get 4c, which implies that c equals 2. Okay. And then if I let x be 0, then I'm just going to get 2 times 0 is 0 plus 4 is 4. So I get 4 equals, that's gone. Here I'm going to get negative 2b. And here I'm going to get 0, right? So that means b is negative 2. And then I think I'm kind of out of luck as far as a is concerned. But at least I can plug these in here. And then solving for a shouldn't be too terrible. So I'm going to say 2x plus 4 equals ax squared minus 2ax plus b is negative 2. So maybe I should have said minus negative 2 times x, so that's minus 2x, and then negative 2 times negative 2 is a positive 4. And then c was 2, so plus 2x squared. Okay, so 2x plus 4 equals a plus 2 times x squared minus 2a plus 2 times x, and then plus 4. Well, I mean, that's obvious, right? But then I can say, well, a plus 2 must equal 0 because there's no quadratic term over here, which means a should be negative 2. And then I can verify that here. If I let a be negative 2, I get negative 4 plus 2 is negative 2, and negative 2 makes a positive 2. So that works. So a should be negative 2. So it's pretty clear now, right? A plus 2 has to equal 0. So a has to be negative 2. Okay. So I've got all my coefficients. I can say now that this expression is really equal to a over x, a was negative 2, plus b over x, b was also negative 2, b over x squared, plus, and then c over x minus 2, c was positive 2. Okay? And that's all there is to that. So, okay. So this one's going to be another negative 2 ln of x. This one's going to be negative 2 times x to the negative 2. So that's going to be a negative 2x to the negative 1 times negative 1, or divided by negative 1. So that's going to take care of the negatives. So I think we're just going to get 2 over x. Man, I should be careful. 2x to the negative 1. If I differentiate, that's going to be a negative 2x to the negative 2. Okay, yep, that works. And then here I'm going to get 2 ln of x minus 2. Okay, so that's that one. All right, so I like the partial fraction stuff. I think it's kind of fun. Although it can get pretty hairy pretty quick. Let's look at another one. So I'm giving us a whole page to do the next 3 problems because I'm not sure how much space they're going to take. But okay, so if I want to do the partial fraction decomposition here, I've got to start by factoring this denominator completely, and I think I can do that if oh yeah, this will factor by grouping, right? If I group the first 2 terms, I can take out an x squared, and I'd be left with 3x minus 1. And from the next group, if I group the next 2 terms, I can't really factor out anything, but I'm just going to call it 1 times 3x minus 1. And so then the factorization, I can factor out the 3x minus 1 now, and get 3x minus 1 times x squared plus 1. So there's the factorization. Now, x squared plus 1, can I factor that any further? And the answer is no, right? You could factor it as x plus I times x minus I, but that's factoring over the complex numbers. Over the reals, this is as factored as that one's, going to get. So we've got a linear factor and then an irreducible quadratic factor. So x squared plus x minus 2 over 3x minus 1 times x squared plus 1 is going to be, this one gets just an a, this one gets a bx plus c. Then I can multiply through by that denominator to clear all the fractions. Oh, and now here I could solve for a if I let x be 1/3, right? That's kind of nasty, but I might as well do it. But then solving for b and c, if I let x be 0, I could solve for, the b would go away, but that doesn't really help me here. I don't know. It might not be so bad. Let me just start by letting x be 1/3. Then I get 1/9 plus 1/3 minus 2. I'm just going to use my calculator. So 1/9 plus 1/3 minus 2. I get negative 14/9 equals 1/9 plus 1, so that's 10/9. So I get 10/9 a. And then here, this part's going to be 0, so that whole thing's going to be 0. So then I can solve for a by multiplying by 9/10. The 9s would cancel. I would get -14/10, which reduces to 7/5. So a equals -7/5. Okay, so that's good to know. If I let x be 0, that seemed kind of promising. Then I would get -2 equals 0 plus 1 is 1, so -2 equals a, which I now know to be -7/5, but I'm just going to write a for now. Over here, the b would be gone, and this would be gone. I would just get c times -1, so -c, a minus c. Well, I know that a is -7/5, so I have -2 equals -7/5 minus c. So then solving for c, let's see, -2 plus 7/5 is -3/5. So -3/5 equals -c. That means c equals 3/5. Okay. What about b? Is there an easy way for me to get b? I can't think of one, but since I already have a and c, it shouldn't be too difficult if I just equate some coefficients. So let me take this a step further. I'm going to have ax squared plus a plus 3bx squared minus bx plus 3cx minus c. So if I equate coefficients, let's see, I would know that a plus 3b, right? So taking it a step further, I guess I would have a plus 3b times x squared. And then for my x's, I would have -b plus 3c x. And then for my units, I would just have a minus c. Okay? And so first of all, I know that a minus c has to equal -2. I guess we could verify that, right? -7/5 minus 3/5 is -10/5, which is indeed -2. So that works out. But then to solve for b, I could use either one of these, right? So if I use the first one, I know that a plus 3b has to equal 1, right? It has to match this coefficient, right? Those two things have to match. So a plus 3b has to equal 1. I know that a is -7/5. So let's see. 1 plus 7/5 is 12/5. Divided by 3 is 4/5. So b equals 4/5. Okay. Putting that all together now, what in the world do we get? So I now know that the original integral I started with, x squared plus x minus 2 over 3x cubed minus x squared plus 3x minus 1 dx is really equal to the integral of a, so that's -7/5, over 3x minus 1. Maybe I'll say this, plus b x plus c over x squared plus 1. Okay. This one's just a natural log. This one is a u sub. I think we'd do a u sub because we've got its derivative kind of sitting up there. Okay. So I'm kind of like, should I even finish this? Well, let's do it. This is kind of interesting. I think I can factor out 1/5. And then I'll call this 4x plus 3. And I wonder if I should clean this up anymore, because I'm thinking, if I do the u substitution, then du is going to be 2x dx, and I've got a 4x plus 3. That's not terrible. I mean, I could actually split this further is what I'm trying to say. So maybe I will. Right? That seems like it'll be a little easier to deal with. Because now actually I could take out the 4, or actually better yet, I'll take out 2 and leave a 2. Then I've got the derivative of this sitting right up there. And I don't even need to do a u substitution. What about this guy? Oh, that's a tangent, right? That's a tangent inverse. Oh, this was a beautiful. I'm glad I continued. It's a beautiful problem. Here, if I did a u sub, let u be 3x minus 1, du would be 3 dx. So I kind of need a 3 here, which I can offset by doing a 1/3 out there, and that would make that a 15. I'm just trying to fix this up so I don't have to do any u subs. So here we go. I think I'm ready to go now. This is negative 7/15 ln of 3x minus 1. That's that first one. Next one's going to be, just to be sure, right? This would give me 1 over 3x minus 1 times 3, right? So I think that works out. What about over here? This is going to be ln of x squared plus 1, right? So I'm going to say plus 2/5 times ln of x squared plus 1. Actually, I don't need absolute values on this one because this is always positive anyway. But yeah, again, just to be sure, I would, if I differentiate it, I'd get 1 over x squared plus 1 times 2x. So that works out. And then this one, I suppose I could have taken out the 3 and just made that a 1. And then it's just 3/5 tangent inverse of x. And there's that bad boy. Okay, so there's that one, right? Not terrible. I still had a lot of space. Okay. Moving on. 2 more. They keep getting worse and worse. That's okay though. Let's see. Oh, what is this monstrosity? So we've got degree 4 plus 1 is 5. So degree 5 in the denominator, degree 4 in the numerator. So this is still a proper rational expression. The degree of the numerator is less than that of the denominator. So we can try a partial fraction decomposition. Oh, and the nice thing is that this is already factored for us. So thank goodness for that. But look, oh man, this is going to be a pain. Here we go. 3x to the 4th plus 4x cubed plus 16x squared plus 20x plus 9 over x plus 2 times x squared plus 3 squared must equal, so for the x plus 2 I'm just going to have an a. For the x squared plus 3, that's an irreducible quadratic, so it has to have a bx plus c. And since it's repeated twice, I have to repeat it again. The second time with the x plus 3 squared. So there's the format of the partial fraction decomposition. Oh goodness, now let's have some fun. We clear the fraction. So only one of these will cancel. So we're going to have the x plus 2 and an x squared plus 3. And here we'll have an x plus 2. All right. Any chance that we'd be able to solve? Oh yeah, we could let x be negative 2. Then that would be gone. That would be gone. We could solve for a. Anything else we could do? I don't think so, because, well, we could let x be 0. That would at least get rid of b and d. Okay, so if we let x be negative 2, then we get 16 times 3 plus 4 times negative 2 cubed plus 16 times negative 2 squared plus 20 times negative 2 plus 9. 49 on the left-hand side. And on the right-hand side, negative 2 squared is 4. 4 plus 3 is 7. 7 squared is 49. We get 49a. Ooh, isn't that beautiful? The rest of it cancels. So a is 1. Okay. If we let x be 0, then left-hand side we just get 9. Right-hand side we get 3 squared is 9. We get 9a. Here the bx is gone, so we'll have a 2 times a 3 is 6 times c, so we get 6c. And here dx is gone, so we have 2 times e, so 2e. And I know that a is 1, so that means I would just get a 9 here, and if I subtract it, I get 6c plus 2e equals 0, or in other words, 6c equals negative 2e. So I didn't manage to solve for e or c, but at least I can make those replacements now if I need to later. Anything else I can do? I can't see anything else that would be super useful right off the bat. So, so I think I have to equate coefficients. So here we go. So here we go. I'm having a hard time motivating myself. But look, this will be x to the 4th. So I'm going to have an ax to the 4th. And then I'll have a 3x squared. I'll have 2 of those. So it'll be 6x squared. So 6ax squared. And then I'll have a 9a. That's that first group. Second group, I don't think I can do this all in my head at once. So I'm going to do bx plus c times x cubed plus 2x squared plus 3x plus 6. Okay, and then the last one's going to be dx squared plus 2dx plus ex plus 2e. Oh yeah, I think I can get some pretty useful stuff. Okay, so this is going to be, if I FOIL, maybe I shouldn't try to do it all in one step. I'm going to make a mistake if I try. So let me do one more. Okay, bx to the 4th, 2bx cubed, uh, 3bx squared, 6bx, then cx cubed, 2cx squared, 3cx, and 6c. And the rest comes along for the ride. All right. Okay, now let's equate some coefficients. So I've got a plus b x to the fourth. So that takes care of my x to the fourths. What about my x cubes? So I've got one here, 2b and c, and that's it, right? 2b and c. So 2b plus c, x cubed, takes care of those. What about my x squareds? I think I've got a lot of these. A 6a, a 3b, a 2c, and a d. They all wanted a piece of the x squared, right? Well, not for e, I guess. My x's, I've got a 6b, a 3c, a 2d, and an e. And then my constants, got a 9a, a 6c, and a 2e. All right, look at that. Okay, now I can equate coefficients. So I know a plus b has to equal 3, right? A plus b has to equal 3. And I also know that a is 1. So 1 plus b equals 3. That means b equals 2. Good. Well, since I know that, I can find c, right? So I know 2b plus c has to equal 4. If b is 2, that means 4 plus c has to equal 4. And that means c equals 0. I know a, b, and c, so I can use this one to get d. All right, so I know 6a plus 3b plus 2c plus d equals, so, oh, what should I do? Maybe a squiggly? Should equal 16. Well, a was 1, so this means 6. B was 2, so this means 6. C was 0, so this means 0. Plus D equals 16. And that means that 12 plus D equals 16, so D equals 4. And then E, I can get from a couple places, right? I could get it here, I could get it here, or I could get it from this relationship. I know that 6 times C equals negative 2 times E. Well, C was 0. So 0 equals negative 2 times E. So let me say 6C equals negative 2E. Maybe I'll put a little star on this one. Right? So 6C equals negative 2E. I now know that C is 0. That means E also has to be 0. I wonder if I could verify that another way, right? So B is 2, so this would be 12 plus 0 plus 8 plus 0. So 12 plus 8 is 20. So the coefficient on my x term should be 20. Yep. Okay, so it checks out. Oh, and then here, A is 1, right? C is 0, E is 0. So this is just 9. So my constant term should be 9, and it is, right? Okay. So there we go. You ready for this now? Okay, here we go. So we've got 3x to the fourth. This one might take multiple pages. Plus 4x cubed plus 16x squared plus 20x plus 9 over x plus 2 times x squared plus 3 squared dx equals a over x plus 2, just make it a dx, plus bx plus c. C is 0, that's nice. So bx plus c over x squared plus 3 plus dx plus e. So that's 4x over x squared plus 3 squared. That's not terrible. We can finish this up pretty quick. This one's just ln of x plus 2. This one is just ln of x squared plus 3. This one, I think I'm going to have to... Yeah, I'm going to do a u substitution. It's just going to be a u to the negative 2 with some constants going on. So that shouldn't be too terrible either, but I'll do a u substitution for it. If I let u be x squared plus 3, du is going to be 2x dx. So I'm going to take out a 2 and put a 2 there. Right? Then I haven't changed anything. So if I let u be x squared plus 3, then du is 2x dx. So this is just du over u squared. Okay, I think I can do that in my head without having to do a u substitution. ln x plus 2 plus ln x squared plus 3 plus, or maybe I should make it a minus, but du over u squared, so u to the negative 2, so that's going to become a u to the negative 1 divided by negative 1. So that's going to be a negative 2 over u, where u was x squared plus 3. Plus c. There you go, in all of its glory. Goodness, should I check this one? I mean, it would be, so negative 2 times x squared plus 3 to the negative 1. If I differentiate, that becomes 2 times x squared plus 3 to the negative 2 times 2x. And so that becomes 4x over x squared plus 3. Yep, that's what I started with before I did this thing, 4x over x squared plus 3. So yep, it works. That should do the trick. Goodness gracious, wow. Well, I still had some empty space though. So I consider that a success. One more. Now on this one, the degree of the numerator is greater than that of the denominator. I might have to pause this to go see what's going on with my dogs. Okay, I'm back. So here we've got a situation where the degree of the numerator is greater than that of the denominator. So before we try to do partial fraction decomposition, we should do some long division. So we've got the numerator divided by the denominator. So when you're doing long division, make sure that you write out all of the missing terms. In this case, we don't have any missing terms, so it's, not a problem. But just as a reminder, right, here's how this goes. So 3x to the fourth plus 3x cubed minus 5x squared plus x minus 1. And then we've got an x squared plus x minus 2 sitting out here. Ooh, running out of ink. And then we ask ourselves, what times x squared gives me 3x to the fourth? And the answer, of course, is 3x squared. So then I multiply 3x to the fourth, 3x cubed, negative 2x squared, and then I subtract. Those are gone. Those are gone. And so then I'll have a negative 5 minus a negative 2. That's a negative 5 plus 2. That's negative 3x squared. Bring down the x. And just to keep my bookkeeping kind of nice, I'm just gonna label this as 0x cubed like that. Okay? Because then I would ask myself, what times x squared would give me 0x cubed? And the answer, of course, is 0x. So 0x cubed plus 0x minus 0, or whatever. You subtract this and nothing really changes, but now you can bring down the negative 1. And this would be a negative 3. We've got negative 3x squared minus 3x and then plus 6. And if I subtract, I'm going to get x plus 3x, so 4x, and then negative 1 minus 6, so minus 7. Oh, my apologies. Okay, so our original integral up here is really the same thing as 3x squared minus 3 plus 4x minus 7 over x squared plus x minus 2 dx. And if we're lucky, I don't think we'll even have to do partial fraction decomposition on this leftover part, because it looks like I can probably break this down into 2 pieces. But then to do the 7 over x squared plus x minus 2, I'd probably have to complete the square here. I might do partial fraction decomposition on it anyway. I think it's probably easier. So let's break that part down even further. So I'm going to say 4x minus 7 over x squared plus x minus 2. Oh, but notice that the degree of the numerator is now less than that of the denominator, so it makes sense to do partial fraction decomposition on it now. I could have factored this as I went. Let me just rewrite. So x squared plus x minus 2 would be x plus 2 times x minus 1, right? So this is going to be a over x plus 2 plus b over x minus 1. That implies that 4x minus 7 equals a times x minus 1 plus b times x plus 2. If I let x be 1, then 4 minus 7 is negative 3. The a's are gone, and I get 3b. So b is negative 1. If I let x be negative 2, negative 8 minus 7 is negative 15. Negative 2 minus 1 is negative 3. And the b's are gone. So then a is 5. Okay. So, my original integral, 3x to the 4th plus 3x cubed minus 5x squared plus x minus 1 over x squared plus x minus 2 dx is really the same thing as the integral of 3x squared minus 3 plus 5 over x plus 2 minus 1 over x minus 1 dx. Believe it or not. This looks much nicer as far as integration is concerned, right? Anyway, the integration is not difficult at this point. This is going to be 3x cubed over 3, so just x cubed. This part's going to be a negative 3x. This part's going to be a 5 ln of x plus 2. And this part's going to be a negative ln of x minus 1. Don't forget your constant of integration. And that My friends, is all I have to say about that.